Thank you for joining us. To start the program, could you provide us with a little bit of background on your work and sort of set the conversation in context, please?
Well, thanks, Judy. I'm delighted to be here. This is a really high-tech event, and I'm glad to see that we're now a global village that I can interact with people from all over the world. It's really wonderful. So I'm here to talk about a new concept. Actually, it's an old concept with a new name, but an old concept whose time has finally come. The name is the Connectome, and if you've never heard that word before, you don't have to feel embarrassed because it's a new word. It first appeared in print in 2005, and it's a word that was coined in analogy with the genome. It means a map of all the connections between neurons in a nervous system or in a brain. And if you want to imagine it, I probably spend too much time on planes, but I think about those pages on the back of in-flight magazines. So imagine that every city were turned into a neuron, and every route between two cities were a connection between two neurons. Then you would have a connectome, except for your connectome, it would be 100 billion cities and 10,000 flights emanating from every city. So a highly complex map that would never fit in the pages of an airline magazine. And more than that, everyone's connectome is unique. So your map and my map would not be the same. And one of the most interesting hypotheses, or meta-hypotheses, that neuroscience needs to test is the idea that your uniqueness, your personality, your memories, your intellectual strengths and foibles, all those things are somehow encoded in that pattern of connections, that map of your brain's neurons.
Well, thank you for that overview. That's really helpful. I will also do a little bit of an infomercial at this point for you, in that anybody who wants to see another talk that Professor Seung has done on the Connectome can find one on TED.com. But before you click over to TED.com, let's ask a few questions. So it sounds like the mapping of the human connectome is a project on the scale of mapping the human genome, but probably at least raised to an order of magnitude, if not several. Is that correct?
Yes, just to toss out some big numbers, your connectome has 1 million times more connections than your genome has letters. That's a lot of information. And so, in fact, we're not even starting to work on an entire human connectome. We'd be happy if we had an entire connectome of a mouse brain. That's already incredibly difficult to find out. And in fact, that's too hard right now. So we'd be satisfied to map out the connections in small chunks of brain, animal brains or maybe human brains. And from that, we could actually learn a lot. We don't have to do an entire brain to learn some really interesting things about neuroscience.
How do you decide which parts of the brain you want to look at first?
Great question. So you're right. The technology is only good. So you could think about it as Google Maps, right? You zoom in to see a particular place more clearly, or you zoom out to see the whole overview. And you can't do both at the same time. So there are low-resolution methods like MRI, like brain scans, which tell us which parts of the brain are involved in certain functions. And then once that's identified, we can go in and look at it with high resolution using microscopy, light microscopy, or the most powerful form of microscopy, electron microscopy. But just for reference here, 1 pixel in a brain scan from MRI is 1 cubic millimeter that I just talked about, which contains 1 billion connections and 100,000 neurons. So there's a whole universe inside 1 pixel in that brain scan you see in the newspapers.
Wow, it's staggering to think about, how you are actually collecting and analyzing that much data. What are the techniques that you use to identify the pathways?
Right, so this is all about the data deluge. So those of you who work in the business and in the tech world know that last year was the year of the big data buzzword. Businesses are just awash in all this data about their consumers, and they want to be able to analyze that data to discover value, to discover valuable knowledge and information. And it turns out that biology and other areas of science are also faced with this big data deluge, and what better place to work on that than MIT, right? So the way that the images are taken is that you have to take very high resolution images because the branches of neurons are so thin, And you take brain tissue, you stain it with you pickle it, you stain it with heavy metals. This is all with a dead brain. You stain it with heavy metals, you embed it in hard plastic so that you can cut it really thin, right? You can't cut Jell-O really thin. You've got to cut something hard. And then you use a device called an ultramicrotome, which is fitted with the world's sharpest knife, a diamond knife whose edge is atomically sharp. You cut slices that are 1,000 times thinner than a hair. Imagine a very high-tech deli slicer. And then you take those slices and put them in an electron microscope, and you image them. You put the images back together into a 3D image, and then you have a little virtual piece of brain tissue, a whole image of every neuron and every synapse between neurons. And then the hard part begins, which is to analyze that data. You've got to trace the pathways, right? The pathways are those branches of neurons. Remember that neurons look like trees? And so their branches are like the wires of the brain. You've got to trace the path of each of those wires, and you've got to find the synapses at which those wires touch. If you can do all that, you'll find a connectome.
Is that done by a human being or by a machine? Can that be done machine?
Great question. So to do it by a human, so no, it's very time consuming for one person to do that. So the only connectome that's known in its entirety is that of a little worm called C. elegans, which has just 300 neurons. And it took over a dozen years to find. And that's because a person had to manually go through all the images and trace those wires. So my lab and other labs have been spending the last 5-6 years on developing AI to do this automatically, right? We love the idea that computers are going to make our lives easier. Sometimes they make our lives tougher, right? We love to complain about them, but we love the idea that it will make it easier. And indeed, AI has gotten a lot better, but it still makes mistakes.
Yeah.
Right, so you know that computers, this is an image, this is a problem of making machines see.
Yeah.
Look at images, and we all know that computers don't see as well in real life as they do in movies, right?
Yeah. Hence the CAPTCHAs.
Hence the CAPTCHAs, hence the CAPTCHAs. So those CAPTCHAs are so hard, I can't even do them these days. So
yeah, they've gotten more difficult,
right.
That's for sure.
So computers make errors, and we need humans to correct the errors of the AI. But it turns out the computer is accurate enough that correcting its errors is faster than doing it by yourself. Right? If you have an assistant who makes a lot of errors, you get sick of it and you'd rather do it yourself. But if your assistant is smart enough, it's easier to correct the errors of your assistant than to do it all by yourself. And that's the point that we've gotten to.
Is this sort of the new field that's evolving called bioinformatics, or
so
something like that? The application of computers to life science information.
That's right. So some people like to use the term neuroinformatics or computational neuroscience. But I think more broadly now, because I call what we're doing citizen science. So we've built a website called iWire, E-Y-E, wire.org, which allows the public to come and play a game of coloring images to correct the errors of the AI and help us map connectomes. We need people to help us. We don't just need computers. And so we're trying to build a community of people who are exploring the brain together. And I call this the grand quest to unite us to explore the jungle of the mind.
So this is what you mean when you talk about citizen neuroscience in your Wired Differently project.
That's right. So Wired Differently is the overall organization that's going to support citizen science. And we're intending to address all kinds of interesting scientific problems, but we need your help.
Yeah. Okay, so questions are starting to come in from our audience. We have a person in California. It's a digits and numbers, so I'm not going to, or excuse me, letters and numbers, so I'm not going to read that. But
that's very MIT.
Yeah, it is. Behavioral studies suggest you have a defined style at an early age and that you become more of what you are as you get older. How do you believe the connectomes change without changing a person's identity?
All right, so this is a great question. I remember I have an anecdote that I gave a talk once, and the next day a woman came up to me and she said, "Professor, that was such a fascinating talk, but what I really want to know is, can people change?" They say that your personality is fixed after your age 6. Is that true? And there was a man standing next to her who looked kind of sheepish. And I thought to myself, lady, what you really want to know is, can my husband change? And you know, I tried to give her some scientific answers, but I think what she really wanted me to tell her is either one way or the other. Either your husband can change or your husband can't change, and she would have been happy with that. But instead, I gave her these wishy-washy science answers. But unfortunately, that's all that science really has to say right now, because we don't know enough about how the brain changes when people change. So when I say that your connectome may be when I say the connectome is perhaps the foundation of yourself, the reason I say that is that the connectome doesn't change as rapidly as the signals that are passed around inside your brain, right? So your thoughts, your perceptions, and so on, those are somehow based upon these rapidly changing electrical signals that are sent by neurons. Neurons are active one minute, not active the next. But your connectome changes much more slowly. And so that's why it could be the basis of the self that changes very slowly, right? We all know that we often have difficulty. If you go to the self-help section of the bookstore, you can see from all those books, we have difficulty changing ourselves, right?
Yeah.
So the way that I lay out this question in my book, so I've written a book called Connectome, How the Brain's Wiring Makes Us Who We Are, and I'm giving an infomercial here, but for reality, you know,
by all means,
we can't really address all these questions in depth. So
yeah.
I really urge you to go and see my book, where you can see these questions addressed in a really more meaningful way. But there are 4 mechanisms of connectome change that scientists have identified. I call them the 4 R's: reweighting, reconnection, rewiring, and regeneration. So reweighting is a change in the strength of an existing synapse or connection. That's the most minor kind of change. Reconnection would be the creation of an entirely new connection or the elimination of an old one. That's a little bit more significant change. Rewiring would be the growth and retraction of branches, like trees growing branches or losing branches by pruning. And then regeneration would be the creation of entirely new neurons or elimination of old ones. And so the battle lines about how much you can change have really revolved around neuroscientists arguing about, do the 4 R's continue in adulthood? So,
what do you think?
Well, everyone agrees, and pretty much everyone has agreed that reweighting continues all your life, and that's why we're lifelong learners. Reconnection, people thought in the 60s that it didn't happen anymore when you were an adult. But now there's a lot of evidence that it happens even in adulthood. The real battles are over rewiring and regeneration. That many neuroscientists in the 80s and 90s had evidence that rewiring stopped when you're an adult, but now there's revisionists who argue that it's still likely. And regeneration happens very little. As far as we know, you're pretty much born with all the neurons you'll ever have, except for 2 exceptional brain areas. But another kind of interesting hope is that some neuroscientists are trying to find drugs that might promote the 4 R's and perhaps even reawaken some of the R's, even if they do stop naturally.
Fascinating. So taking another question from our audience, Doug from Temple University asks, synaptic connections between neurons can vary considerably in terms of strength and character, excitatory, inhibitory, modulatory. How can brain mapping technologies take these subtle variations in connections, which may be critical for plasticity, into account?
Yes. So I think what Doug is rightly pointed out is that not all connections are the same. Not all neurons are the same. And if we just reduced it to a map that looks like cities and lines, then that might be losing some important information. And so you're quite right. So when we image the neurons, we can actually tell a lot from those images. So one is that different neurons have different shapes. And we can classify those neurons by their different shapes, like you classify different species of trees. And other neuroscientists study the properties of each type of neuron, each species of neuron, see how their synapses work, see what neurotransmitters they use, and so on. And so that's how we can actually combine the information from those measurements of different kinds of synapses with the connectome, by recognizing the synapses and neuron types by their appearance.
Fascinating. Horton from The Office. Suppose that you could obtain a near infinite resolution connectome. You could now say, assemble this to determine what someone thinks. How does this fit within an ethical framework?
Yes. So some people think that my goal is to simulate the brain. They may have heard about the Blue Brain Project, a very famous partnership between a neuroscientist named Henry Markram and IBM, Big Blue. And IBM gave him I think, a nice discount on a supercomputer, and he was going to use that to simulate the brain of a human. And he's indeed made grand claims that he's going to simulate an entire human brain within 10 years. And I think already 2 years have passed.
That seems unrealistic if it took 12 years just to define the connectome of, what was it, C. elegans?
That's right, C. elegans, that's right. Well, so one of the criticisms of that project is that they're using made-up connections. They don't really have realistic kind of pattern of connections to put in their simulation. So, but the natural question you would say, well, suppose we succeeded in finding a human connectome and we handed it over to our friends at Blue Brain, would they then be able to simulate an entire brain? And I think it's safe to say that that's very controversial. We don't know. Some people argue that a lot more information would be needed than just that map of hubs and spokes, right? That you need additional information about the particular molecules, how they're distributed across the neural membranes. You need to know the detailed shapes of all the neurons, so on and so forth. Whereas other people argue, myself included, that perhaps, although we might need a lot of additional information besides the connectome, that might be, fractionally speaking, much less than the information in the connectome itself. So the connectome plus nice dynamical models of the neuron types, which are relatively compact, that might be enough for a simulation. But I think that remains to be seen. We'll, in the next few years, as we find connectomes of small chunks of brain, maybe we will discover how much about the functionality of the brain is coming from the connectional pattern and how much is coming from other sources. Both are important.
Yeah, it's sort of a foundational ethical question about artificial intelligence,
right?
And whether or not you can simulate a human being.
That's right.
In a machine.
That's right. So I'm not really worried about the ethical questions because we're so far from succeeding. But you're right that big ethical questions would be addressed, would come up. And my book talks about these kinds of fantastic questions in the last 2 chapters when I take on the transhumanists. They're the people who want to alter human nature, either by freezing themselves in the practice of cryonics or by uploading to transfer their minds to computers, to live happily ever after in a simulation.
But all machines break eventually.
Oh, yes. You don't have confidence. Well, there's always a backup, though, right? You have a backup, don't you?
I don't know. That's what people have told me when my computer crashes.
Yeah, okay.
There is no solution to that problem.
Okay.
So Fabio B. Fabiab in Freiburg asks, do you foresee your work helping to lengthen the life of people?
Well, the transhumanists are the one who actually want to live forever by uploading themselves. But I'm on a shorter term, I'm really hoping to improve the lives of people who have mental disorders. So, I mean, that's also a long-term kind of proposition because the brain is so complex. But I'm less worried about lengthening the lives of people than of trying to help people who are having problems right now. And so I could talk more about the question of how the connectome is related to psychiatric disorders, if that's interesting.
Yeah, I think that would be very interesting.
Okay. Well, you've all heard about, I think the diseases that get a lot of press are things like Alzheimer's disease and Parkinson's disease, where you have neurodegeneration. So when you take the brain of a person who died with Alzheimer's disease, then you can see that their brain's damaged. Neurons are messed up, they're dying, and so on and so forth. But what's puzzling is that in many psychiatric disorders, which are quite marked in their behavioral, in the way that people behave, like schizophrenia, right? People are crazy with schizophrenia. I'm sorry, I shouldn't use that word, but who are that's an extreme word, but who have many obvious difficulties in behavior. If you look at their brains, there's been 100 years of failure to find a clear and consistent neuropathology. There's some reports of statistical abnormalities. Let's say slight differences in size on average when you average over 100 schizophrenics and 100 regular people. But there's nothing that can be used as a distinctive marker for the disease, unlike, say, infectious diseases, right? So we know that infectious diseases, you look at the culture and you see the microbes, and bam, you can diagnose it. So what could be wrong with the brain? We believe schizophrenia or autism are brain disorders, but what's wrong with the brains? And one really intriguing hypothesis, I'm not responsible for it, other people have posed it in the literature, is that the neurons are healthy, but they're connected in an abnormal way. Imagine I went
So the synapse is abnormal.
Well, not the synapse, it's just the pattern of the connections. Imagine I went to the back of your stereo.
Okay.
And I just disconnected some of the wires and I reconnected them in a different pattern.
Okay.
Your stereo doesn't work anymore. You take a casual look, you have no way to tell. Every individual connection is working properly. It's conducting electricity. It's just not wired up in the right way, right? So it could be that there are these connectional abnormalities in the brain that our technology has never been able to detect. And the hope is that new technologies will reveal them. That's the big quest. And in fact, for citizen science, the goal of Wired Differently is, one of the goals is going to be to mobilize the public to search for connectopathies, which would be, I think, a totally game-changing discovery if we could succeed.
Yeah. So this goes to the question we were talking about before the program started about clinical applications of this specific work and how you can make a decision to explore a certain part of the brain.
That's right. That's right. You're exactly right. So other neuroscientists have to tell us which part of the brain they think is abnormal in these disorders, and then we got to look there at the detailed wiring to see if we can see something really abnormal. We are really excited about that. We want to raise public interest and, of course, find the financial support to carry this out.
Now, a related question that has come in from Bill in Cape Coral is the connectome a physical connection that could be broken by a physical injury to the brain? It sounds like it is.
That's right, yes. So you could, any of the wires in principle could be broken. I'm not sure that that's typically what happens. Typically, if we're talking about traumatic brain injury, which is still very poorly understood, the initial impact of an injury may not be to sever wires. I mean, of course, if you drive a knife into the brain or something like that, you would.
Right.
But if it's a blow to the head, what happens is that some kind of damage occurs. And then the damage causes the wires to degenerate.
So it could be like a swelling where it cuts off blood flow and then the wires atrophy or whatever.
Some kind of complex chain of events that in which damage lead, and the same is true of a stroke. Stroke doesn't kill, as far as we know, stroke doesn't kill neurons immediately. It kind of cripples them, and then they die a slow, lingering death afterwards.
But the connectome then is a network of physical connections.
The connectome is very physical, and if you go online to iwire.org, you'll see or wiredifferently.org, you will see images. Also, the website from my book shows beautiful images of the brain, and you can see inside. The TED Talk also, there's so many graphics. I can't describe it in words, but you see these are real things. These synapses, the neurotransmitters, the wires of the brain, they're not figments of someone's imagination. They're real. And we find them by cutting up brains and imaging them. So they're physical things. And this is really, in the end, this is really the big mystery of neuroscience, which is how does mind come out of the physicality of matter, right? And we're looking at that physical structure.
Violet in Arizona asks, as the mom of a son with autism, my intuition since his infancy was that his brain was wired differently. And 10 years of therapy have helped him rewire. Is there any research or evidence regarding autism and the connectome?
There is none so far, I would say. I think there are people trying to use MRI to find differences in the gross connectivity of the brain. So there are connections between regions, which is kind of a zoomed out map. But the work on the connectome at the neuron scale, at the cellular scale that I'm talking about, we want to do that. And of course, I'm in the middle of writing grant applications to raise the money to do that kind of work. I want to collaborate with a colleague of mine at MIT who's done some really brilliant work on creating animal models of autism. So Guoping Fong, he has taken a genetic abnormality that's associated with a kind of autism, and he's put that into mice. And the mice have social deficits. They do repetitive behaviors. And so the big challenge is now to find out what's different about these mouse brains. And hopefully that will tell us something about what's different about human brains in the case of autism. I mean, it's great that the therapy has helped him rewire. One of the challenges of connectomics is to understand how rewiring, or the 4 R's in general, help us learn to improve our behaviors. Whether we have autism or whether it's just any of us who are trying to improve. We all want to improve, right? And in the end, every kind of important personal change is about the brain.
Absolutely. So another question has come in. You presented your work at the World Economic Forum Ideas Lab at Davos a few years ago. And we are curious about what aspect of your work seems most interesting to business and economic leaders.
Well, business and economic leaders are, of course, just like us, and they are just fascinated by the brain. They all have one, and it's one of the biggest mysteries. So at the World Economic Forum, one of the hilarious things is that they would say to me, "Oh, I'm so bored with these business talks. I hear them all the time. I'm so glad I came to hear about the brain. It's something new," right? So we were kind of like the entertainment at the World Economic Forum with the MIT professors. In terms of their other interests, of course, psychiatric disorders are a huge economic drain on our society, and I think that leaders are aware of that. And it's one of these things where you are not going to have a quick fix. It's not like we understand the brain and bam, we're going to discover the therapies now, because in fact, it's not widely known that antipsychotics and antidepressants, these drugs that are highly prescribed today, they were discovered by accident in the 1950s by chemists, not because we understood the brain. So it's, but neuroscientists are hoping that because neuroscience is making progress, that there will be rational means of discovering new drugs and new therapies. But we still need a lot of basic research to get there.
Well, I see that our time is coming to a close. So I'd like to offer you an opportunity to tell us something that we have or have not asked about. You know, what else do we need to know about the work that you're doing and how it might impact the future?
Well, I think that MIT is a wonderful place to be doing this work. I've got a great lab of students and postdocs and even undergrads. The undergrads were really excited to help us out in IAP in launching the Citizen Science website. So it's just tremendous to be working with MIT students. And so I would suggest that if you guys want to contribute, go to iWire. There's an active discussion forum. We're looking for partners who can actually build up the educational part of the site, partners in gamification to make the game more fun. We want this to be a grassroots kind of effort. So I encourage all of you to contact me and use the site, and hopefully we can find some way to come together and understand the brain. So there's people love to ask this philosopher question, like, is the brain complex enough to understand itself? And so today my response is, well, maybe not, but if we put our billions of brains together, maybe that's going to be enough to tackle this question.
Yeah, and I keep, what's running through my head as I listen to you talk about this is there an MITx course that could help to build that
That's a great idea. That's a great idea. Well, in general, I haven't really looked much into MITx, but in our opinion, citizen science is a new model for education that's a little bit different from MITx in that we want to tightly integrate learning about the brain and discovering something about the brain.
Yeah.
And having a good time.
Yeah.
In the process, right? So that's tall ambitions. We just started, and so I think that's a different kind of model of education where it's not delivery of sort of standard lecture fare, but a tight integration of education and discovery.
That's terrific. Thank you so much, Professor Seung. On behalf of the MIT Alumni Association, I want to thank you and our viewing audience for joining us. We encourage you to continue discussing these issues in this work on our blog, Slice of MIT, by following the link that will appear on your screen. And please join us for the next Faculty Forum online webcast scheduled for early May. Thank you.